Welcome to the lecture on nuclear instrument for Bsc VI students in 6.1 paper by Ms. A. Shirly Jones, Associate Professor, Department of Physics, Veerashaiva College. In this chapter of nuclear instrument, let us first learn about Geiger-Müller counter. A Geiger-Müller counter is a detector of alpha or beta or gamma particles. It is basically belonging to the family of proportional counters. It consists of an ionization chamber, and the ionization is independent of primary ionization, and hence the instrument does not distinguish the type of radiation that enters the chamber. But however, it is well and very efficient in order to detect either alpha or beta or gamma particles. Now let us look at the construction of GM counter. The GM counter essentially consists of a GM tube, an amplifier, and a resistor to detect the counter. The GM tube consists of a central electrode of tungsten wire of about 0.01 centimeter in diameter. The outer electrode is a metal tube within a glass envelope acting as an electrode and a container. The metal tube is well insulated from central electrode. The GM tube is filled with a gas mixture of 90% argon and 10% alcohol. I'll tell later why 10% alcohol at a pressure of 10 centimeter mercury. The schematic diagram is as shown in the figure. Now let us learn the theory at which this instrument works. Whenever an alpha particle or beta particle enters the GM tube, it ionizes the gas. Usually halogen gases are taken and the positive and negative ions are formed. When the voltage source is at zero or low voltage, the ions doesn't move. But when a proper voltage called starting voltage or threshold voltage is given, the ions formed move towards the respective electrodes, constituting a current, and hence we get an output voltage across the resistance. This voltage is amplified and a sufficient height of the pulse register a count C in the counter. However, within the starting voltage or threshold voltage, no counts are registered. Now, as the voltage is raised, the counts first increase, remains constant over a range of voltage, and then suddenly increases as shown in the graph. Now this graph, when it is drawn between the applied voltage and the counts per second, is called as GM characteristic. So what is GM characteristic? It is the graph and the curve obtained between applied voltage and the counts per second is drawn. Now the curve or the GM characteristic has got two regions. One is the plateau region, another one is avalanche region. Now the plateau region is the range of voltage in which the counts per second remains constant over a range, and the midpoint of the plateau region is called as operating voltage. Now the avalanche region is defined as a short voltage at which there is a sudden increase in counts per second due to the breakdown of covalent bonds of the gas, forming an avalanche of electrons. Now other important parameter of a GM counter is the operating voltage, and every counter is made to work at operating voltage. Whenever you want to experiment using GM counter, you must know first its operating voltage. Then what is this operating voltage? It is the voltage of the counter at which the counting rate is independent of a small changes in PD across the GM tube. The counter, when operated at operating voltage, the electron producers reach the respective electrodes at a definite interval of time, that is 10 raised to minus 7 seconds. But the heavier positive ions get excited and form a sheath on the axis electrode. This depresses the electric field and the instrument becomes inoperative. Also, the positive ions reach the cathode to detach the secondary electrons from it, and the atom is excited state eject photoelectrons, giving fresh avalanche. What is avalanche? Group of electrons which are formed again and again. Thus, continuous avalanching takes place and is a self-perturbing phenomenon. To control this, an important process called as quenching is done. Then what is quenching? Quenching has got few important parameters. Namely, the first one is dead time. Dead time is the time in which the GM tube becomes inoperative due to the presence of positive ion sheath around the anode and is equal to the time taken by the positive ion to reach the cathode. Next, another important parameter is paralysis time. It is the time in which the supply voltage is reduced by 200 volts at definite time intervals successively to enable the counter count at high speeds. Now, the paralysis time would be somewhere around 300 to 500 microseconds. Now, if N0 is the observed counting rate, then the true counting rate is given by a formula. N is equal to N0 divided by 1 minus N0 tau, where tau is called the paralysis time. This GM counter is very efficient in counting the particles reaching it. Various experiments can be done, like you can find the energy of the particles which are entering also, we can find half-lives also, we can use statistics to count the counting statistics you can find, and it gives you much information of the radioactive element and the energy radiations coming out of it. So it is very much in use and popularly used to detect radiations. Now let us go to another counter called as scintillation counter. The number of alpha particles are counted by this scintillation counter. They are detected by the scintillation counter. Now, this uses a principle of scintillations produced on the fluorescent screen, that is zinc sulfide fluorescent screen. Now, what is this fluorescent screen? It is a screen which is coated with fluorescent material like zinc sulfide, what you see in cathode ray tubes and all. Now, the visual counting is converted into a current by photomultiplier tube and associate circuit. The schematic diagram of a scintillation counter is as shown in the figure. The diagram consists of a phosphor crystal and is fixed to the photoemissive face of the photomultiplier tube through a lucite connection. A light sheet of aluminum foils serves as a reflector. This assists in directing light to the photocathode. The current produced is amplified in terms of voltage. The voltage pulse is discriminated for the height and the number of counts are recorded. Well, let us know more about scintillation counter in its theory. When incident radiation falls on phosphor crystal, electron-hole pairs are formed. The number of pairs formed depends upon the energy of the incident radiations. The atoms or holes return to their ground state by emitting photons in the blue or ultraviolet region of the optical spectrum. The photons strike the photocathode, causing ejection of photoelectron. Thus, photoelectrons are focused with various reflectors as shown in the figure and fall on the plates of dynodride procedure. Produce more electrons and an electric pulse is formed. The multiplier stages are many, usually 10 to 14 stages. The pulse is amplified and counted by a scalar registered. And the schematic diagram you see here, incident radiation falling on the phosphor, and the phosphor converts it to a light pulse. The light pulse falls on the photomultiplier tube, then it converts that into an electrical pulse. That pulse is amplified, then it is fed to a register to register a count. Now all this instrument works on the phenomenon called as scintillation. What is the scintillation? It is a characteristic light emitted whenever a charged particle is incident on a fluorescent screen located with a fluorescent coated with a fluorescent material. So you see that you get a visual scintillation conversion to electric pulse and registering an account. Now let us go to another important aspects in nuclear instruments. Those are accelerators. Now what is an accelerator? An accelerator is a device which accelerates the nuclear radiations. Usually the radiations are emitted with certain energy. The energy of beta is very greater, gamma is still greater, alpha is less. But for research purposes and for various other applications of nuclear radiations, highly energetic radiations are needed. Now earlier accelerators used to accelerate the radiations to 30 MeV, but later to 200 MeV, and now we have got thousands of MeV. There are various nuclear instruments which are used in order to accelerate these nuclear radiations. In fact, the Big Bang theory works with hadron accelerator, where it is accelerated to 10,000s and millions of revolutions per second. That means high energy is needed. Basically, the first accelerator what was discovered was linear accelerator, where we had cylindrical pipes of increasing length along the same axis enclosed in evacuation chambers which are connected to very high voltages. Now the way in which the accelerator was connected was that odd number pipes or cylinders are connected to positive terminal of the accelerating potential, and the even cylinders are connected to the negative potential, so that at every end of the pipe, it gets an acceleration and it gets further acceleration in the next pipe as the AC input goes on increasing. However, this linear accelerator, though it is the first one, it's believed that this accelerator is between two cities in US, the first accelerator, but there were many disadvantages. First thing is, it is too clumsy, too lengthy, too heavy, covering kilometers of distance. And the second one is providing vacuum all along the lengths of the linear accelerator is difficult. Very high voltage alternating voltage should be given, so that the power supply was given all along the length at definite distances. So people thought of Though it was the first, it could accelerate it, but people thought of some other accelerators, and then came your cyclotron, which is very, very efficient. It has reduced its size, and I will see the advantages later. But let us learn about cyclotron. Now, what is a cyclotron? A cyclotron is having a principle. Now, what is that principle? The positive ions move in a spherical path of increasing diameter by the application of constant magnetic field. The device is a magnetic resonance accelerator. The positive ions are accelerated when they cross the gap between two hollow metallic cylinders called as Ds. The time of transit of ions between the electrodes and the frequency of the electric field are in phase, so that the ions gain energy whenever they cross the gap between the Ds. The electric field provides energy, and the magnetic field guides the positive ions in circular orbits. In 1931, E.O. Lawrence introduced the principle of cyclotron to accelerate positive ions. Now, what exactly it consists of? It consists of a flat semicircular metal base called Ds, D-E-E-S or D apostrophe S, placed so that the diameter edges are parallel and slightly separated from each other. They are placed in a closed vessel having a gas at a pressure of 10 raised to minus 6 millimeters of mercury. At the center of the Ds, the source of ions is kept. The vessel is placed in the midst of a strong electromagnet, that is, a magnetic field of the order of 20 kilogauss, whose direction is perpendicular to the plane of the Ds. The ions are taken out of the chamber with the help of a negative electron with the potential of 50 kilowatts at the periphery. The diagram cyclotron is as shown in the figure. Now let us learn about the cyclotron. Now this cyclotron, in cyclotron, positive ions are accelerated. Let us take positive ions first. They are emitted by an ion source. The ion, when enters the DD1, which is negative first, the magnetic field makes it to move in a circular path governed by the equation. The magnetic force acting on a charge moving with a velocity v in a magnetic field is BeV, and because it moves in a circular path, the centripetal force which is essential to make it to move in a circular path is mv square by r. Therefore, BeV is equal to mv square by r, or r is equal to mv by Be, where m is the mass of the positive ion, v is the velocity, b is the external uniform magnetic field, and of course e is the charge. Now the time taken by the ion to move the circular path of radius r should be equal to the time taken in which the polarity of the D's changes. That is, D2 should be negative. The ion starts and moves towards D1, which is negative. It goes in a circular path of radius r, and by the time it comes to the end of the D, the beside D should become negative. D2 should become negative. If T is the time period of the radio frequency of generator, then half of the time of the oscillating potential should be equal to the time taken for 1D. Therefore, circumference is 2 pi r. Half D circumference means pi r. Therefore, time is equal to pi r by v, or T by 2 is equal to pi by v, and let us substitute for r there. You get T by 2 is equal to pi m by b. Thus, the ion, every time it moves in a D, is accelerated and moves in D with increasing radius, and finally is deflected at the circumference using a deflector at very, very, very high voltage. Let us see some other parameters. Let omega be the angular frequency of the revolution. Then omega is equal to V by R. Therefore, V by M, V into BE by MV, or omega is equal to BE by M. Therefore, the frequency F is equal to omega by 2 pi, or F is equal to BE by 2 pi M. The above frequency is called as cyclotron frequency, which should be equal to the frequency of radio generated, FO. FO is equal to BE by 2 pi M. This is also called as magnetic resonance frequency for the magnetic resonance frequency for proton is 1.25, B deuteron is 0.76. Also, it is found that the energy is proportional to B square. Now, what is a Betatron? A Betatron is essentially a device accelerating electrons to an energy of 300 MeV. The principle with which the Betatron works is the electrons are accelerated by the electric field induced by changing the magnetic flux in the stable orbit linked with the orbit and changing the field. Now, the construction of the Betatron is something like this. It consists of an annular vacuum chamber made up of glass or ceramic in donut shape. Donut. This chamber is kept in between specially shaped electromagnets. The inner surface of the donut is coated with thin layer of silver to avoid surface accumulation of electrons. Now, the principle on which the Betatron works is the oscillatory current in the primary coils of electromagnet produces an oscillating magnetic field which produces an induced EMF which accelerates the electrons. Now, let us know the working of the Betatron. The electrons after preliminary acceleration, that means from the source of the radioactive element to beta particles are ejected, but they are given a preliminary acceleration, and after preliminary acceleration they are injected to a stable orbit in the donut by means of an electron gun. The electrons are produced only during the quarter cycle. Now, the magnetic field around the arrangement exerts a Lorentz force and which will guide the electrons to move in circular orbits. The magnetic field accelerates the electrons by keeping itself alternating in time and inducing EMF. The action of Betatron is same as that of a transformer. Now, let us look at the analytical treatment. Let B bar be the average value of the magnetic field within the arc enclosed by the stable orbit of radius r0, and at the orbit the magnetic field is B0. The flux linked with the orbit is phi is equal to pi r0 square beta average. Therefore, the induced EMF according to electromagnetic induction is EMF is equal to minus d phi by dt. Now, the work done on the electron in one revolution is therefore equal to minus q e. Therefore, the work done on the electron in one revolution and is equal to a tangential force acting on the orbit, that is minus QE is equal to 2 pi R0 FT. What is FT? Tangential force. Therefore, the work done on the electron in one revolution is minus QE is equal to minus EE. This should be equal to the tangential force FT. Therefore, FT is equal to E divided by 2 pi R0 into d phi by dt. For a stable orbit, B0 EV is equal to mv square R0. Now consider B0 EV is equal to mv square by R0. mv is equal to B0 E R0. Now, at any instant, the momentum of the electron is given by P naught plus dP is equal to E B naught R naught plus delta R naught. Therefore, the force is equal to, according to Newton's second law, is equal to dP by dt. That's equal to E R naught dB naught by dt. Also consider minus E is equal to 2 pi R naught EFT. Therefore, d phi is equal to 2 pi R naught square into dB naught. Therefore, dB dash is equal to dt is equal to 2 dB naught by dt, or B average is equal to 2B0. This is called as the condition of the Betatron. The magnetic field applied is twice the magnetic field at the D's. Though it could accelerate the electrons to higher energies, Betatron has got it. Well, what are they? The first one is it is bulky because it uses huge amount of iron in pole pieces as pole pieces in magnets. Second one is because of the large air gap, the reactive power runs into 1000 kilowatts. To minimize this, Betatron is connected to a capacitor bank. The third limitation is the magnetic field which guides small amount of iron is used, and rest is to provide the acceleration. The fourth limitation is there is radiation loss as high energies are obtained. Thus, there is a limit to 300 MeV for electrons. The maximum energy the electrons which can be energized is 300 MeV. And the fourth one is it is too costly. However, India has a beautiful Betatron in the University of Pune, and the electrons are accelerated to a very, very, very high voltage. Now, these accelerated electrons are used for various research purposes, and we should have such accelerators. Now, that's it. It covers all the instruments, few are detectors and few are accelerators.